Assalamu alaikum. May the peace of Almighty God be with you all. You are welcome to my class. Today we are going to discuss thermal expansivity. What is thermal expansivity? From the word thermal, it means heat. So expansivity, expansion is the one of the effects of heat. There are several effects of heat, such as change in temperature of the body subjected to heat, such as change in the physical properties of the substance or object subjected to heat, physical properties such as density. When I mean density, is how light, to a layman, say how light or how heavy an object is. It is mass per unit volume of a substance. Physical properties such as color and other effects of heat such as thermionic emission, when electron is emitted from the metal surface as a result of heat. So we are actually picking thermal expansivity, which we can say is the change in the shape and size of a body as a result of application of heat. So the change in position in the shape and size of that body can be of three. It can be linear, dealing with just the change in the length of that object. It can be area, dealing with change in length, the breadth of the object. And it can be volume, which deals with change in length, the breadth, and the height of the object. So we are going to take them one after another, starting from linear expansivity. Linear expansivity is the fractional increase in length per unit length per degree rise in temperature. The fractional increase in length per unit length per degree rise in temperature. Take for instance, I have this amount of solid material, for instance. This is the initial length before application of heat, which I can call this as L0, original length of the substance, from this place to this place. Now, when I now subjected heat, remember at this particular, it has its own temperature, maybe at room temperature or a little bit above room temperature. Now, if I subject this to heat, let's say the temperature at this moment when it has not been subjected to heat to be θ1. After subjecting it to heat, maybe the length increase this much. Let's assume the length increase this much. Now, the whole here to this place become my final length after application of heat. So I can say from here to here is what? L2. Now remember as well that since I have applied heat, then temperature will what? Will increase. So at this particular point in time, when the length has increased as this much, then the temperature there, let us call it what? θ2. Now you believe me that there is what? An increase in what? In length. Of which amount? How do we get the amount of increment? The amount of increment, which we can call increase in length, we can call extension, we can also call change in length. Change in length with this sign, so change. Anytime you see delta symbol, it shows what? Change. Change in length is going to be what? Final length L2 minus what? Original length L0. And there's going to be a change in temperature as well. So change in temperature, delta theta is equal to theta 2 final temperature minus what? Theta 1 initial temperature. Are we together? Now remember linear expansivity. So linear expansivity is represented with a symbol known as alpha. Alpha. You can write it like this. Alpha is the increase in length. What is my increase in length? Which is what? L2 minus L0. L2 minus what? L0. All over the original length times what? Change in temperature, or temperature rise, which is theta 2 minus what? Theta 1. So the linear expansivity is known as the coefficient of what? Expansivity, which is paramount to different materials. Every material have a particular response to what? To heat. Some, if you subject two materials to the same temperature, their response is going to be different. So we have linear expansivity for different materials. Some materials, example, iron, has a linear expansivity of iron is 0.00012 per degree Celsius, right? Yes, I think 0.00012. 1, 2, 3, 4, 5. Yes, this is it. Per degree Celsius or per degree Kelvin. Change of unit in this does not matter. Degree Celsius and degree Kelvin is the same as the unit of what? Linear expansivity. So if you have a value that is in degree Celsius, don't bother yourself to convert to what? Kelvin. Are we together? So why that linear expansivity of brass is about 0.00019 per degree Kelvin, per Kelvin, yes, or per degree Celsius. So what is this one telling us? For this, it's telling us that when iron is subjected to what? To heat, it will expand as much as 0.0000012 when heated through what? Through 1 Kelvin of temperature. While this brass, when heated through 1 Kelvin or 1 degree Celsius, it will expand as this much, 0.000019, which shows that brass expand more than what? Than iron when subjected through the same temperature. This idea is used in our thermostat. It's used in our thermostat. Thermostat is just a device for temperature regulation. They have two dissimilar metals of different what? Of different linear expansivity attached side by side that is used in temperature what? Regulation. You found it in your oven, you find it in your electric pressing iron, etc., fire alarm system, and the rest of that. Are we together? So now, from this analysis, under linear expansivity, we have this formula, you have to keep in mind that linear expansivity alpha is the change in what? Change in length, final length, minus original length, all over original length times what? Change in what? Temperature, which is theta 1, theta 2 minus theta 1. If that is taken, remember that L2 minus L1 is the what? Amount of extension. So I can say that alpha is equal to what? E all over L naught. Why this? I can represent it as what? Change in what? Theta. Is that clear? So which simply means that my E extension is L2 final length minus what? Original length. Are we clear? From here, no, from this, I can make L2 subject of the formula. From this one, I can make my final length subject of the formula. How do I get that? Alpha is what? L2 minus what? L1 or L naught all over L naught change in what? Theta. So if I cross multiply, I'll have what? I'll have, which implies L2 minus L naught is equal to, this multiplied by this gives me alpha L naught change in what? Change in theta. When this one goes to the other side, it will become what? Positive. So I have L2 is equal to alpha L naught change in theta plus L naught. So you can see now L naught is common in both sides. So which implies L2 is equal to, by the time I bring L naught outside, L naught into bracket alpha change in theta plus what? Plus 1. So I can write it as L2 equal to L naught into 1 plus what? Alpha change in theta. So we can, anytime you ask to find final length, you can quickly write this, or we can make use of this direct. That is all for now. In our next class, we are going to bring 1 or 2 work examples to showcase how to apply this formula in solving problems related to linear expansivity. Thank you. I hope you enjoy this class. We meet in our next class.